Hey, how's it going there? This is Blaine Keckler. We're going to be talking about electron beam machining, and so let's get started. Alright, maybe not. Let's see if this is loaded. Hey, thanks for joining my seminar on electron beam machining. My name is Blaine Keckler, and I'm going to tell you guys a little bit about electron beam machining. So to get started, the way that the electron beam actually creates the cutting process is very similar to the just laser beam machining. Depending on its parts and everything like that, you can see a very similar result. The way that the actual electron beam works is by creating a whole lot of kinetic energy and then releasing it all at once. And what this does is it bombards the part and basically vaporizes the material. So if you want to get into the actual parts and description of what each part does, we can go ahead and do that. The electron beam uses a voltage source from a direct current voltage supply. This voltage supply can be anywhere from 25 kilovolts to 5 megavolts. It's a varying range. It depends on what you're trying to cut, what heat you're trying to achieve, how fast you want these electrons to actually be produced. So to begin, the cathode grid, or the electron gun, basically is what creates these electrons. It's all housed in a vacuum sealed chamber. This chamber kind of just makes sure that there's no air particles or anything in the air that will actually get in the way of the electrons shooting down towards the material. The cathode grid can actually reach between let me go back. The cathode grid can reach between 2500 to 453 or 4532 degrees Celsius. The next part that we're going to talk about is the annular bias grid. The annular bias grid is the next component going from the top down. What this does is it channels all of those electrons that are shooting out, and it basically forms a more precise beam to bombard the part. It collects the electrons and keeps them from diverging from one another, and produces a very precise beam, very small precision beam. The next part is the magnetic lens. What that does is it reflects the electrons onto itself to make an even more precise line for even finer line of a beam. The precision of the cut can actually magnify down to as small as 2 millimeters, and it just gets smaller from there. The next part is the electromagnetic lens. The component basically does what the uh, previous component did, the magnetic lenses. It magnifies it even more to the point of where the beam can actually reach as small as 100 micrometers. The next part is the actual workpiece holder. This part is usually ran by a CNC machine, so nobody would really do it by hand. It would be something that was programmed in to actually move the table along with the beam being stationary. It can move in the X, Y, and Z coordinates so that it can pretty much manufacture any type of cut that you would need. The next part we're going to talk about is the actual applications of the electron beam machining in the manufacturing processes. The most interesting one that I found was the aerospace manufacturing to deal with NASA. The researchers at NASA developed a solid fabrication process using the electron beam known as EBF, or electron beam manufacturing freeform fabrication. So what this does is the electron beam for the freeform process feeds a metal wire into a collection of a molten metal, and it pulls up, and they can melt down pretty much any type of metal that they would need. Anything going from any type of alloys like that they would use in space. This is also concealed in a vacuum, just like the regular electron beam manufacturing tool. The process of using the electron beam freeform machine is it's much faster when it's needing to remove material from a part or adding it on, like I said, with the welding type of process. With this process, the developers can add or subtract any type of the material that they needed to without having to manufacture the whole part itself over again, which is super convenient, super nice. Like, it's way faster than having to forge something or whatever they would need to do to make, a satellite or some type of rocket. I don't know. Some of the advantages of the EBM is that the electron beam is actually super, super small. It can make crazy small cuts. It's very, very precise, like I was saying before. It goes down to about 100 micrometers in some machines. After the product is actually finished, you don't need to. There's no machine finishes that need to be done after the cut is made. So once it makes that hole, it's perfect. There is nothing that you need to grind off. There's no sanding. There's no chiseling. Nothing that you need to take off. And it can also cut through pretty much any material that you would want. I mean, even the highly reactive materials I saw that you could cut through. Those are some big things that a lot of manufacturers would love to have and not have to worry about. Some of the main disadvantages: the machine itself is very, very big. It weighs about 3,500 pounds. It's not going to be easily moved. You're not going to be able to get some guys to go in there and move it. You're going to need a forklift of some kind, and you're going to need a specialist to be able to hook it up and make sure everything's running correctly with the vacuum and everything. That leads into my next point of it's extremely hard to make a vacuum environment for the beam. You're not going to be able to do this yourself. You're going to have a specialist come in and make this for you in your facility or your plant. And my last point for it being a disadvantage is that it's crazy expensive. It can range from $80,000 to $800,000. I would assume the ones at NASA might even be more. I'm not sure, but they're extremely expensive, and not every company has that type of money to be able to use. So, yeah, that's my presentation, and I hope you like it.